So at home, make sure you have your slides in front of you for this. All right. So as I mentioned yesterday, Barajas. I don't know. I don't know how to win. So it's a very big deal for our solubility rules to be in your brain. All right. So hopefully this looks familiar to you. You don't have to squint. You have it in front of you from your printout. You should. Anyway, no, you printed it out yourself at home before class.
I don't have a printer.
So you copy it down first then. Come on, AP, an hour out of class every day is the expectation. How many of y'all are doing that?
I do it the hour before this.
I guess no more questions on the smoothie.
So we've got our rules here for solubility. A couple things I want you to know. First off, cross out number 3 because we are just counting fluorine as a normal halogen with everybody else. All right, so number 3 is not going to apply to you.
Like the one that says FR solid.
The one that's right in front of you, so you're not squinting.
No, I am. I'm saying number 1.
Yeah, number 3. Rule number 3.
What does that have to do with fluorine?
With fluorine. Oh, I said no fluorine. I said fluorine.
Yeah, he said fluorine.
I said fluorine. That's rule number 3. Mentions fluorine. Rule number 1 is what we call the Big Daddy rule, and it's important because if you ever have 2 rules disagree with each other, Big Daddy wins. All right. It'll bruise your eye. Am I right?
Big mommy.
So, no one cares what she says. So, Big Daddy wins no matter what, so keep that in mind. And it states that the alkali metals are pretty much always soluble. All right, so anything over there in group 1 and when it's bonded ends up being soluble. And then ammonium that is bonded into a salt. The first issue, the first rule that really you're going to have to focus on is rule number 2, which talks about the halogens. All right, and lucky for you though, you get to write down that Hal hugs Aggies pretty badly. Because if you write down that Hal hugs Aggies pretty badly, it'll help you remember the exceptions. Remember how the exceptions work. It says things like, I like everyone in this room except Kathleen. All right? So it's love everywhere, except there's that one thing that's just no love at all. So the halogens are soluble unless they're bonded to, and look at Hal hugging Aggies pretty badly. You've got your mercury, you've got your silver, and you've got your lead. All right, so it's hidden in the acronym there. Now, while we're talking about solubility, though, let's make sure that we remember the labels connected to them. What when something was soluble, what label did it get? AQ. All right, meant that it was soluble. I feel like you do it on purpose. And then what do we give something that's insoluble? The S. Telling us that it's solid. All right. Hey, what was the other name for a new solid that forms during a reaction?
Precipitate.
A precipitate. You weren't wrong, because we say it differently. All right. So some basic things to keep in mind. Now let's keep going through our list, though. Rule number 4 covers nitrates and a couple of polyatomics. Nitrates show up a lot, so it's good for your brain to know that nitrates are always soluble. But rule number 5, the sulfates, well, they cause quite a problem. It's all right, I'll damn. But as long as you know that Sol can bag hads pretty badly in Sri Lanka, Argentina,
I love that.
then you're good to go. So if you're sitting in the AP and someone hears you whisper to yourself, Sri Lanka, Argentina, then that's a huge Cummings win. Sulfates are soluble unless they're bonded to, all right, and here's where you can find it. We've got barium in bag, mercury in Hag, lead in pretty badly, strontium in Sri Lanka, silver in Argentina, right? Did I do that good? I don't know. It was good. It was good. I haven't spit all day, so I could do that. What did you say, Diego? I mean, it exists. I don't know. Maybe, but probably not. Barajas, what was the question?
I was saying you can say my name.
Oh, okay. So anyways, these acronyms, yes, now make a better acronym, whatever. Maybe that's terrible. But do what you have to do because you need to know these exceptions. And then number 6 takes into account that actually the majority of other polyatomics are automatically insoluble. So you've got, but pay attention to Big Daddy though, because if they're bonded to an alkali metal, then they are soluble. So keep all of those things in mind as we continue. I'd like you to practice a few though. So go ahead and do all 3 of these. I just want you to label them with the proper labels. Hey, maybe try not looking at the solubility chart, but I get that you need to right now. You're just learning how to get them in your head. I don't. You're the only student because I've been talking to kids. You're the only student that can't get it on your phone. I don't know why. It hurts. Pull it up. Pull it up. Just don't cheat the system. We're gonna draw cards.
Mr. Cummings, I also heard you say like something about like the solubility thing in a packet. I don't know.
A solubility thing in a packet. Did you watch an old video?
No. Like you were saying like
Yeah,
yeah.
we talked about it yesterday.
So you didn't give us a packet.
You said you give us a packet.
That's one we got last year.
Oh, I was referring. I misspoke. Then I was referring to. I mean, that's it.
Oh, okay.
That is the solubility chart. I can print y'all out some if you want me to, but you can get it off that slide. That's the entire chart.
Oh, okay.
Wait, so it says Big Daddy and Gold is all that's true. Does that include the record too then? Or it's just-
Yes, yeah. Nitrates are always, no matter what.
1 and 4.
Right.
But 1 and 4 are like they disagree. What would be the-
They won't disagree. I can't think of an instance that they will. So what are we dealing with here? We got some silver nitrate. And we got some sodium chloride. Definitely got some lead bromide. Whoa, that is fun. Let's go to cluster 3, seat 2, Aspen. Oh, I didn't put Aspen out. Amara, you're Aspen, right?
Yeah, I said it's soluble.
She said it's soluble. Is she right?
No.
It says except.
She is right. Nitrates are always soluble. All right, nitrates are always soluble. Yes.
Is that because it's both? Oh. Okay. Good then. Never mind.
Who's it supposed to go to? Alyssa, have you been Aspen yet?
Yeah, I'm asking my set there.
Have you been Aspen yet? All right, it's back around. Anyway, let's head over though to seat 6, 3, Aspen. What did you get for sodium chloride?
Soluble?
She said soluble. Guys, could y'all have done sodium chloride without looking at the solubility chart?
Yeah.
All right, if you're smarter than this, then just be smarter than this. I mean, this was asking you, does salt dissolve in water? Yes, it does. All right, salt is aqueous. All right, but yeah, what that is, that's a halogen. All right, the halogens are soluble unless they're bonded to. They have exceptions, but not an alkali metal, for sure. All right, because those are always soluble. Let's go over to cluster 4, seat 3. Hey, 4-3, what did you get for the last one? She said insoluble. Is she right?
Yes.
Right, because bromine is usually soluble. However, we got pretty bad, right? Pretty bad. It's pretty bad.
I get it.
It's an exception. Questions? Now, what we need to do with these is something that is 100% going to be on the AP. Or not necessarily with these, but realize that the test isn't going to just say, is this soluble? All right, it won't be that direct. The AQ and S's are going to show up as just an extra point on something larger. Your ability to recognize and put them in properly. One of the very common something largers are complete ionic and net ionic equations. So we need to make sure that we're sharp at those because they show up on every single test. So I'm going to show you how to write them. A couple things to keep in mind is that when doing the complete ionic, those are the really long ones that are less fun to write. But subscripts become coefficients when you're counting moles. I'll show you what I mean in a second. I just want to say it so I can refer back to the fact that I said it. For the net ionic equations, which are the shorter ones, we have what are called spectator ions. A spectator ion is when during a reaction you have ions on the reactant side that are the exact same on the product side, so they're not really doing anything. And I'll show you what I mean in a moment. So, let's write some ionic equations together. This is going to require some translation and product prediction, so if I do something that doesn't make sense to you, it's important that you stop me. All right? I'm happy to explain what's happening. But I'm going to go ahead and translate this. So, potassium chloride is KCl, all right, is being combined with plus lead 2 nitrate. Lead 2 nitrate. I know that He is soluble because the halogens are soluble. There's no exception happening there. I know that He's soluble because nitrates are always soluble. Are we okay so far? Now, this is double replacement, all right? It's not an acid and a base, so if you remember, double replacement was where we just switched the cations on the other side. So in other words, potassium will be with nitrate over here. And lead will be with chlorine. Yes?
You said that the one with nitrate is soluble,
Yes, because all nitrates are soluble.
but it has
That's part of but it's part of Big Daddy. Big Daddy. Now, we need to predict the solubilities of our products. All right? What's the solubility of potassium nitrate?
Yes.
All right, yes is a weird answer, but soluble because all nitrates are soluble. What about lead 2 chloride?
No.
Insoluble. All right, because pretty bad showed back up attached to a halogen. We all right?
Yes.
Now, we want to balance the equation because an unbalanced equation is always wrong. So we can do that real quick. There's 2 nitrates, so I want there to be 2 nitrates. There's 2 potassiums, so I want there to be 2 potassiums. Now everything is balanced. 2-1, 2-1 mole ratio. In order for us to write what's called a complete ionic equation, we need to show the dissociation patterns of everything in the reaction. Now, we went over dissociation reactions yesterday, so this should be real simple, except there's just more stuff here. All right? Now, what's important to understand, though, is everything in a double replacement that is aqueous is going to dissociate. But that precipitate down there, well, it's not. When the reaction's over, the precipitate is the solid that's sitting there. It's not dissociated and floating around in the solution. It's a solid that's just sitting in the solution. So while we do this complete ionic, we're not going to dissociate anything that is solid, anything that is liquid, anything that is not aqueous. So let's do some dissociation. Watch how I do this. Starting here, I'm going to show that we've got 2 K pluses. I've pulled apart the reactant. All right. And we also have 2 Cl minuses. Both of them are aqueous. All right. So all I did was pull him apart, showed that there was 2 from that coefficient. All right. But we have more reactants. All right. We have 1 lead there. All right, the lead looks like that. How many nitrates?
2.
There's 2 nitrates. That's what I mentioned earlier, is that the subscripts that are counting moles have the ability to become coefficients, like it did right there. So there's all of my reactants. Now let's do the exact same thing to the products. All right, we've got,
Why is the aqueous?
because all nitrates are aqueous. So in this case, anything that's bonded to a nitrate will dissociate. So if he's going to dissociate, now lead's not bonded to anything. So if lead is now an ion that's freely in the solution, he's going to retain his original charge. So here we've got 2 potassiums and 2 nitrates. What's going to happen to that other product? He's not going to change. Solids don't dissociate. Precipitates don't dissociate. So plus PbCl2 solid. So all I did was I identified everything that could dissociate and pulled it apart into its pieces.
So does that mean every time there's an S in the original equation it's not gonna stay the same?
Correct. Now, that's a complete ionic, which is a bummer to have to write. There's another thing called a net ionic, which takes into account spectator ions. As I mentioned before, a spectator ion is something that stays the same on both sides of the equation. Watch, they're easy to find. Like you see the 2K plus? Yeah, those are spectators. Do you see the 2 NO3 minuses? Those are spectators. Now, those were all the spectators. The net ionic will simply just put the leftovers into its own little equation. So I got 2 Cl minuses plus 2 PBs. I'm sorry, 1 PB, but with a charge of 2. Yields PbCl2 solid. Original equation, complete ionic equation, net ionic equation. Did you say good job? Thanks. Chemical reaction, complete ionic, net ionic.
Which one do you usually ask for that?
It depends. The net ionic is more useful in chemistry, so it would make more sense for them to do this, but a lot of you won't get to the point where you feel comfortable just writing it from this, which means y'all will like feeling good about crossing out your spectators. It's hard for you at this level to practice so much that you can go from here to here. So, will you show the next one so that they can practice one? Here's one for you. I'll translate it for you because I don't want that to be what slows you down right now. It shouldn't be. You should be good at the translation. But I will help you translate and balance. I want you to be good at the equations. Silver nitrate is reacting with magnesium bromide. All nitrates are aqueous. Halogens are aqueous unless they're bonded to stuff, but magnesium's not an exception. Ion swap, magnesium is going to marry nitrate. Silver is going to marry bromine. Little wife swap. Elements are crazy, y'all. All nitrates are soluble. halogens have exceptions. Is AG an exception?
Yes.
Aggies, right? Stupid Aggies. Who likes maroon? Whoa. Gig 'em.
Let's go Astros.
Wait, so when it says BR is soluble.
Yeah, bromine is soluble unless it's bonded to
Oh, okay.
silver, mercury, lead. All right, guys, see if you can write both equations. I'll give you a couple minutes to get going. Complete ionic and net ionic. Make sure you balance the equation.
Wait, so it's not already balanced?
It's not already balanced, but it's very easy to balance. It won't make you think, I promise. Heaven forbid you have it. What's up, little birdie? Robin joke. Yes. Guys, some of you are getting confused when an exception dissociates. All right? If silver shows up by himself because he's dissociated, he's already dissociated. He's going to still be aqueous. He was already identified as aqueous, so don't go look at rules. We've already said that silver nitrate's going to split apart. Therefore, silver's going to split apart, be aqueous, and get his charge. It's your notes, so whatever, but there'll be Schoology questions about it. I believe in
Robin, did you say it's already balanced?
Yes. Yeah. Yeah, the coefficients can create coefficients, and the substrates can create coefficients. If the substrate is counting moles, not part of a charge cross. Or polygon.
Swell them up and it's that.
When it's solid, you don't put the charges right. This is
Right, exactly. Yeah, because there are no charges.
I take biology 1.
For bromine, when it dissociates, you wouldn't write BR2 since it's that.
Right. Yeah, no, because the diatomics don't matter here while it's got its charge.
Okay.
No Brinkelhoff today, ladies and gentlemen. I'm going to start just writing. You can keep working. I'm just going to get stuff written up here on the board.
Yeah, I know.
Oh, I don't know why I put that.
Wait, did it tell you now?
Kick her out.
Kick him out first.
Kick her out.
Is that way to tone
You can see that. They've grown dead on it.
Yeah.
Kick her out.
But I mean, no, she said I confused myself.
So many people leave this class room. It's getting to change.
No, it's not.
There's two actors.
I've got a complete ionic up here. Make sure that there's nothing weird in your opinion.
If you put a that be right?
Yeah, I mean, this is the only way to show it. If you did anything different, then no, it's not correct.
But like if you put the 2 to the VR, put it underneath the subscript.
Yeah, no, that's no good. Always. All right, so let's find our spectators. It looks like we've got a spectator here and a spectator there, which means my net ionic is going to be 2Ag plus aqueous plus 2Br minus aqueous yields 2AgBr solid. All right, you would just take those guys and shove them together. Yes?
Where did the 2 come from?
From here? From my balanced equation. So my original mole ratio is 2 to 1 to 1 to 2.
The 2 before the yield, it's because it's the bottom.
Oh, with this one here?
No, the bromine, but it's before the yield. You're talking about after. It's over here. There we go.
Oh, I get that.
So remember, yeah, the subscripts that are basically, one way to loosely say it is if the subscript is not part of the polyatomic, it's been assigned to it or the element, then it's going to become a coefficient. Brinkelhoff has no play here. There are no free elements. Oh, no, that's because of magnesium. Now, I want to point out that what happens in a double replacement reaction if both products are predicted to be aqueous? Who remembers?
They combine.
What?
They have a fun time. It's not hard.
What? If both products are predicted to be soluble, what is true about the reaction?
It's decomposing.
It won't happen. It's a no reaction. Because realize what happens. If there's no precipitate forming or predicted to form, then everything is a spectator ion. They would all cross out at the end. And if that happens, then there's nothing happening. That's why it's a no reaction. All right, the dissociation will still take place, but everything will just float around in the solution. They're not going to create new compounds. No reaction. If they're both aqueous. Isaac, they want you, not right now though, let me finish. Thanks.
Wait, so what was the final question again?
The final answer was him plus him yields him. I just didn't rewrite it. Okay, will you go to the next paper, not to the next problem? All right, so what about a different type of reaction though? Now, y'all are going to get all wrapped up in this aqueous dissociates, but neutralization is different. If it's neutralization, well, that's when we recognize it as an acid reacting with a base. Now, a couple things to remember about neutralization. The products are super predictable because it always makes salt, which is any ionic compound, and it always makes water. But here's where some more of yesterday's skills are going to matter. Listen. A strong acid or base completely dissociates. We knew that yesterday. A weak one doesn't. What that means is if you're writing your ionic equations and you run into a weak acid, it's going to be treated the same way as a precipitate. It's not going to dissociate. So we're going to have to remember how to tell the difference between strong and weak acids and bases.
Weak acids don't dissociate.
Weak acids are aqueous and will not dissociate. See, I got you.
What if it's a non?
Then it's not neutralization and this doesn't apply. All right? Can you go to the first example on the next page, please? So let's keep going and do some neutralization. Working together, sodium hydroxide is NaOH. All right? Hydroxides are commonly insoluble, but Big Daddy says that if they're bonded to an alkali metal, soluble. All right? Phosphoric acid, as I'm sure rolled right off your brain. All right, now The prediction of products here, like we said, we always know what neutralization makes. So if you switch the Na and the H, it looks like double replacement, but it's always going to make salt and water. So you can see the water form when the H joins the OH, and you can see the salt form when the Na joins the PO4.
I have a question.
Yep.
Will there ever be a solid on the reactant side?
Yes, but not in this unit. So we're good. All right, so a few things we need to look at before we start. First off, we need to predict the solubilities of our products. Careful here. What is the solubility or the state of matter of water?
It's the universal
Liquid. Yeah, guys, if you form water, that's a liquid. Liquids will not dissociate, as mentioned earlier.
With the solvents, right?
What? Aqueous is a solution, which requires something dissolved in water.
So aqueous is a liquid?
It's what
Aqueous might be a liquid state, but it's impure.
Wait, water is the solvent.
Water would be the solvent here. All right. What about sodium phosphate? What's its solubility?
It's solid. Just kidding.
It's aqueous. Because Big Daddy says
Oh my god.
that if you bond it to an alkali metal, it's automatically soluble.
Is that?
Like nothing can change it. It's automatic.
No, that's a cursive L. And water has breast cancer. Okay.
No.
Now, well, what about now? Since it's neutralization, strong versus weak is a big deal here because remember, weak acids and bases won't dissociate. So, sodium hydroxide, strong or weak? Strong. If a base is bonded to a group 1 metal, it's automatically strong. All right. What about phosphoric acid?
Weak.
Strong.
Why?
I don't know.
Yeah, you just talk. It is weak. Why is it weak? Because it's not. Because what?
They're not.
Because there's only one more oxygen than hydrogen. Remember, you got I bring clay, which doesn't apply here. All right, and then we have our oxygen rule. So this is weak, which means he won't dissociate. Are you ready?
Most aqueous are strong because they have an alkaline metal in front of it. Most have. Did you say if it has a?
I mean, I know, you just got to watch for those alkalis. Yes, those alkali metals will automatically go AQ. All right, here we go. Let's start with complete ionic. All right, he is strong, so he will dissociate. Oh, balance, dun, da, da. It looks like we need a 3 there for the sodiums. Bump, 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 and a 3 here for the water. Now there's 6 hydrogens. 3 and 3 is 6 hydrogens, 3 oxygens, 3 oxygens. Boom, but you already knew that. Okay. It takes you, quit doing that. If it takes you longer to balance, whatever, but I hope you get faster. All right, so let's dissociate. We've got 3 Na pluses and 3 OH minuses. And what am I going to do next?
They don't.
Leave it alone. Weak acids don't dissociate. H3, PO4, aqueous, and that's the part that messes with y'all. Oh, but it's aqueous. Y'all, we've got a lot of rules interacting with each other here. That's what makes this annoying. I get it, but it's happening.
So what the heck are you liquid?
I'm sorry? Okay. Here we go.
And then
To the other side, hey, what's water gonna do?
Liquid.
they have the
It's not gonna do
It's gonna wet.
It's gonna do nothing.
Ah, disgusting.
All right? But then that salt will dissociate. Not if it's hot. No, yeah, liquids don't dissociate.
Can this look a normal L?
But doesn't that look like a 1?
Can your capital L of it?
No, that looks like liters, sir. And liters is very associated with water. Don't do that.
So they'll
So we all know it's.
Here, I mean, you can do this little thing that people do. That's the other.
I can't do that either.
That looks like a 1.
No, that isn't. Okay. I'm okay. Now, let's do net ionic by getting rid of my my repeats. Hey, look, there's a spectator. There's a spectator, and they know most spectators now. So we have my net ionic as this.
Did you never get closer?
I don't even know which.
It's disgusting.
Why? Because your hand remains bad.
What do you think?
That's not fair.
It's
It's not fair.
literally just going like this.
How are we doing?
Right there.
On FRQs, would we get points off if we don't put alias and?
But it's usually just it's just 1 point though. It's a minor deduction. But yeah, they want you to keep the states of matter everywhere.
Wait, but does a complete ionic equation take the coefficients to the net?
Oh, like he doesn't.
Yeah. So guys, these coefficients can be created by normal coefficients or mole counts that have been assigned as coefficients. I mean, as subscripts, which didn't happen anywhere. Oh, it did happen here. See, like this guy didn't split up, but phosphate said, well, hey, there's 3 hydrogens. So if he would have dissociated, it would have been 3H there. All right. But here, that 4 is a part of phosphate. It doesn't become a coefficient. Phosphate always has that 4,
Parentheses doesn't.
and then outside would.
If NA didn't both have 3, you wouldn't cross them off.
Right, you wouldn't. But they're, because of the way balancing works, that's not going to happen in that way.
Yeah.
I know you don't, but like if you did dissociate the H and the O, would it be 3 times 2?
No, it would be 3 H2s.
Do you keep it 2?
I mean, you don't do that to water.
But like if you did do
Wrinkle
if you were
off.
on
Wrinkle
NA,
off.
3 PO4.
Like would you multiply them together?
Yeah.
There's no wrinkle off.
What is water?
Yeah, no, there's no Brinkelhoff there. Let me verify. I don't believe it would be 6, but let me find out.
It has a minor in chemistry.
You want me to lie to you and just pretend I know everything?
Yeah.
Oh, no, I don't do that. I'm happy to tell you I don't know everything. I don't.
Reach towards the camera like this.
Dang it, I wanted y'all to try one, but we only had, well, here, let's do a little bit of one. Show that next problem. Now, I want to point out, hey, for those of y'all that printed out the notes, I changed it from hydrochloric to acetic. Actually, just watch. I just want to show you something. Just watch so at least we can get it on the video. So, acetic acid, it's different. It's not acetic acid like you can see at home. I changed it to hydrochloric. If you do acetic acid, is acetic acid weak or strong? Is acetic acid weak or strong? Automatically weak because it contains carbon.
Yeah.
Carbon-containing acids are weak. But look. Hydrochloric acid, weak or strong? Strong. All right, I bring clay. And that is reacting here with potassium hydroxide, weak or strong? Strong, because potassium is alkali. All right? Without working it out, here's something that can save you a ton of time if you will trust it. Anytime a neutralization is strong, the net ionic will always be H plus OH minus yields water.
I knew it.
Now, you can go through the steps to verify if you don't trust it, but this is an absolute. If you decide that it's a strong acid reacting with a strong base and you're asked to do net ionic, it's always the answer. We got a computer day tomorrow. Y'all have a great day.
Extra credit.
Top of the black tray.
Okay.